Hi everyone, this is Himadri working as assistant professor in the Department of Mechanical Engineering in RMK College of Engineering and Technology. So today I am going to discuss about Hume rothery rules, phase diagrams and isomorphous phase diagram. So first we will see the Hume rothery rules. So the Hume rothery, he proposed some factors for forming the solid solution. So these factors should be considered before making a solid solution. So we can see one by one. First one is crystal structure factor. So here both solvent and solute are having same crystal structure, then only we can form the solid solution. Otherwise it is not possible. So here copper and zinc both are having same crystal structure. So we can form the brass alloy. So this is the first factor. Now we can see the next factor, relative size factor. So here the atomic diameter of solvent and solute. So both are diameter, it is less than 15%, then we can form the solid solution. But it is greater than 15%, it is not possible. So best both solvent and solute atoms having similar in size, so easily we can form the solid solution. So next one is chemical affinity factor. So in chemical affinity, so the more the chemical affinity of two elements, so then it is not possible to form the solid solubility. So the chemical affinity of two metals, it is less, we can form the solid solution. Otherwise it will form the intermediate phase. So this is about chemical affinity. Next is relative valency factor. So here one atom it is having large valency and another atom it is having the small number of valency electrons. So the high valency it is dissolving in a small amount of lower valency metal, and lower valency metal it is dissolving in more amount in higher valency metal. So example is in aluminum and nickel alloy system. So here the nickel it is having the lower valency, it is dissolving only 5% of aluminum, but aluminum it is dissolving only 0.04% of nickel. So these are all the Hume rothery principles. It will be considered before making the solid solution. So all these factors it will be satisfied, then we can form the solid solution. So next is phase diagram. So the phase diagrams are very important. So after forming the solid solution or alloys, we have to know at what temperature the phases are changing from liquid to solid, and what is the microstructure of particular alloy at respective temperature. So we have to see all these things in the phase diagrams. So the solidification of metals or alloys we can be clearly mentioning in the phase diagrams. So first we will see the introduction in phase diagrams. What is component? Component means it is a pure metal or it is a compound. Example, copper, zinc or copper zinc alloy. We can call it as a alloy. And next is solvent. Solvent means it is a major proportion in a solution or major component in a solution. And solute. Solute means it is a minor component in a solution. or it is a dissolving element. So system means it is a, we can form the various alloys from different elements. So this one we can call it as a system. Next, solubility limit. So here, what maximum solute that will be dissolved at a particular temperature. So this is called solubility limit. So next is phase. Phase means it is a homogeneous physically and chemically characteristics in a structure. So we can call it as a part with homogeneous physical and chemical characteristics. So one phase system we can call it as a homogeneous phase. So some of the systems it is having two or more phases, we can call it as a heterogeneous or mixtures. So it will be happen in metallic alloys and ceramics and polymers. So we can call two component alloy means it is a binary alloy system. So three components alloy we can call it as a ternary alloy system. So coming to microstructure. So the microstructure is, so the alloy microstructure, it is depending majorly on at various temperatures. So at one temperature it will give some microstructure, at another temperature it is the microstructure it will change. So the microstructure is specified by the number of phases and composition and arrangement in that space. So normally a binary alloy, we can take any alloy, two alloys, two elements. So it is a single solid solution, or it is a separate pure components, or two separate solid solutions. So this is about microstructure. Next, phase diagram. So phase diagram means it is a graphical representation of various phases for a given composition with respect to the temperature. So here in y-axis we can have the temperature, and x-axis we have the composition of the alloy, and here pressure we are considering as a constant atmospheric pressure. So now we can draw the phase diagram. So this is called phase diagram. So equilibrium phase diagrams. Equilibrium means we can call it as a slow cooling and slow heating. So we can call this as also constitutional diagrams. So here it will represent the relationship between the temperature and the composition and quantity of the phases at equilibrium. So this is called equilibrium phase diagrams. So why we have to know about these phase diagrams? What is the importance? So what is the importance means? So by using these phase diagrams, we can develop some new alloys, and we can select some particular metals or alloys for product design and in different applications. So we can develop different alloys from this phase diagrams. So and then here it will shows the phases at different compositions. So at what is the weight percentage of composition and with respect to the temperature. So this is for importance of phase diagrams. So at any temperature we can see the what is the percentage of composition, what phase it is existing, whether it is liquid or solid or liquid plus solid. So you can identify from the phase diagram. So before this phase diagram we can see the cooling curve. So cooling curve means, so we can draw the cooling curve with respect to the temperature versus time. So here we can take the metal. we can slowly heat up to some temperature, then slowly cooling to the room temperature. So here what will happen means, at constant temperature, so the metal, entire liquid, it will convert into the solid state. So here for a pure metal, so it is having the constant temperature. So this one we can call it as a pure metal cooling curve. So here it is entirely it is in liquid state. So here it is in solid state. So at this temperature it will convert from liquid to solid. So here at this temperature the heat is released from the melt at constant temperature. You can call it as a latent heat of fusion. Now for binary alloy, binary means two elements, two metals or two elements. You can take two metals and then we can heat up to some temperature, it will be converted into liquid solution. Now slowly you are cooling at this one point of temperature, it will start to solidifying, so the freezing will begin. So then slowly it will increasing at one point of temperature, the entire freezing it will complete. So here the liquid it will be converted to the solid at this temperature, but here it is not a constant temperature, it is in during the decreasing temperature liquid is converted to solid for the alloys. So this is the difference. For pure metal it is constant line, for alloy it is in a inclined line. So now we will see the cooling curve for binary alloy. So before drawing any phase diagram, first you do the experiment, that is called cooling curve. You can take the composition percentage. So here example I am taking percentage of composition 0% B, 100% A, and then from left to right. So here 100% B, 0% A. So in between we are having the various compositions. Now with respect to temperature, so I will take 0% B, 100% A. I will heat slowly up to some temperature. It will be converted to liquid, then slowly cooling to the room temperature. At some constant temperature, liquid will be converted to the solid. So this is for pure metal. Now you take the 10% of B, 90% of A. So during slow cooling, at this point the freezing solidification will begin. Slowly the solid particles will increase. At this temperature entire liquid it will convert it to solid. So like this we are having the various compositions. So now we can connect all these points. This is called freezing starting points or solidification starting points, and then we can draw one line for solidification ending points. So now this red zone we can call, here it is entirely it is in liquid phase. So this green zone we are having the transition zone, that means here both liquid plus solid, both the things will be present. And then this blue region entirely it is solid phase. So now we can see for isomorphous phase diagram for binary alloy system. Here we can take it as a two metals, it will be completely soluble in both liquid and solid state. We can call it as a isomorphous phase diagram. So before drawing any phase diagram, first you do the experiment, that is called cooling curve we can draw with respect to temperature versus time. You can take at different compositions and then you do the experiment. Slowly you can heat. You identify the solidification starting point and ending point. Again you can take example here, copper and nickel. So I am taking 100% copper, 0% nickel, 20% nickel, 80% copper. Like this I will take it at different compositions. I will do the experiment. I will finding the solidification starting point and ending point. Now whatever I told previous slide, so you can connect all the solidification starting points in one line. We can call this as a liquid S line, and we can connect all the solidification ending points. We can call this as a solid S line. So here it is entirely it is in liquid phase. So here it is L plus alpha, liquid plus solid. So here it is solid phase. So this is called isomorphous system. So these are all the various types of phase diagrams. First, components completely soluble in liquid state and completely soluble in solid state. We can call it as isomorphous. But insoluble in solid state, we can call it as a eutectic reaction type 1. Partially soluble, you can call it as a eutectic reaction type 2. And then peritectic reaction. And then eutectoid and peritectoid transformations. So we can discuss later on one by one. So now today we have seen about isomorphous phase diagram. Now we will see the lever arm principle. So here in lever arm principle, two rules are there. First one is chemical composition of phases. So here in this phase diagram, you want to find the chemical composition. At any temperature, you draw the horizontal line to the boundaries of the field. So it will meeting the liquid S line and solid S line. So from this we can draw the vertical line to the x-axis. So here you can identify the what is the composition percentage. 10% of B, 90% A. So here it is 26% of B, 74% of A. So next one is rule 2. We have to find the relative amount of liquid and solid phase. So now here at any composition weight percentage, you can draw the vertical line to the phase diagram, and at any temperature you draw the horizontal line. So it will divide this line into two parts. This is called tie line. So now this one we are considering as a tie line. So you want to find the liquid percentage. So liquid percentage means this is the liquid S line, this is the solid S line. So we have to take this portion Mn by total length Mo into 100. I want to find the solid phase. Solid means, so this is the solid phase. We can take it into opposite fulcrum, that is called No by Mo into 100. So now example from this phase diagram. So I am finding at 80A, 20B. So I am finding the liquid phase is 62.5, solid phase is 37.5%. I have calculated. So total it is 100%. So like this, at any composition, at any temperature, you can find the percentage of liquid and solid. So from this lever arm rule, so at the alloy composition of 80A and 20B at temperature T, we are having the two phases, liquid solution 74A, 26B. It is constituting 62.5% of entire liquid solution. Solid solution, it is having the 98, 10B. It is having the percentage is 37.5%. So this is called about lever arm principle. So like this, for any phase diagram, we can apply the lever arm rule. You find the percentage of liquid and percentage of solid. So today we have seen about what is a phase diagram, what are the types of phase diagram and isomorphous phase diagram. Thank you all.